All right, everybody's back. Okay, we will go back to Jupyter Hub, and let's hope things are still running. All right, can people hear me? So the next piece of things is where we transition to NiPipe workflows. And we kind of call this the world's quickest introduction to NiPipe because we really can't do justice in an hour. But hopefully we can lead you through some concepts so that as you can play with things, you can do things. If we go back to the Jupyter Hub and click on repos, there is a branch called NiPipe tutorial. And we can click that and click on index.ipynb. So the NiPipe tutorial is actually quite extensive. This has been 90% of this is created by Michael Notter, who is in Switzerland. And it goes through various different concepts and components of NiPipe. It uses a Docker container to run things, and you can either use the current container that we're using right now, even when you go back, or you can build your container with NeuroDocker, or you can use the container that Michael points to run this tutorial. So you can run this offline on your computer at any point in time. We're going to cover sort of basic concepts at a superficial level. We're going to talk about all the pieces, but we're not actually going to run those notebooks. The only notebook we're going to run here is going to be the NiPipe Quick Start. If we go through that quickly, then we'll leave a challenge for you after that notebook to construct your own workflow. The NiPipe Quick Start has nothing to do with neuroimaging, and so that's one of the things that I want to talk about a little bit with respect to NiPipe. Note. So NiPipe consists of three pieces. It's a fairly lightweight thing. It has interfaces, which wrap around existing neuroimaging tools. It has a workflow engine, which has some semantics that make your life easier. And it has a set of execution plugins. And this is much like the interfaces don't cover all the interfaces. The execution plugins in this figure doesn't cover all the execution plugins. Allows you to run the same workflow independent of whether you're running it on your laptop, running it in a cluster, or making use of HPC resources. And I would say 80% of all effort in NiPipe has gone into creating the interfaces. So this involves studying each tool and understanding what inputs it requires, what inputs are mandatory, what inputs are dependent on each other, the kind of thing that you don't necessarily get from the help of that tool itself. And so, yes, NiPipe focuses on these neuroimaging tools, and we've used adoption policy that involves if somebody's interested in an interface, they contribute an interface, and we bring it into the fold. So if we look at the NiPipe help and click on documentation, we now have, I'm not going to try and blow this up, we have interfaces from over 40 or 50 packages available via NiPipe. And for any given interface, let's take a look at one of the FSL interfaces. Let's say preprocess. Click on a simple one, bet. It does a few things. So this is help that you can get both on the command line, but also through the online forum. It tells you, there's a link to code, and that will take you to the exact place in the GitHub repo where this interface is defined. It tells you which command it wraps for command line interfaces. We also have native Python interfaces which don't wrap any command. Sometimes it will give you links to the documentation of the original interface. That's something that we have to keep working on. It's not always the case. It gives you a simple example of how you might use one of these interfaces. And then the part that really takes a lot of work is making sure that each of these interfaces have their inputs well described and the help well described. So let's take a quick look over at bet, and it says for bet the only mandatory thing you have to give it is the in-file argument. If you notice, there are names of things. They may refer to flags, and we can take a quick look. So for example, the center argument uses a flag called -c. So you don't have to specify the flags. NiPipe will build that kind of command behind it. For NiPipe, semantic clarity was important. So every input and output has a name. So now we can go down and look at outputs. And every output has a name. So, and that's something that's really not available for most things. When you when you run a command, you're running the command, and then it creates a bunch of files on the file system. It doesn't categorize those files in any meaningful way. You have to interpret what those things are and deal with them, right? And this is what makes writing things like shell commands hard, because you have to know every piece of things, and you have to say, when I run this command, this file is produced with this file name pattern, and I can use this file name pattern to push into my next command. The idea for data flow is that you can stop worrying about that. Because we can use named inputs and outputs, the outputs pipe in automatically to other inputs. Okay, so let's go back to the tutorial. So there's a fair bit of documentation around it, but let's go through the concepts through this notebook called NiPipe Quick Start. And as I mentioned, this notebook doesn't use any imaging function. This helps you understand the semantics of the data flow concepts of NiPipe, and we'll walk through this a little bit. So let's do what we did earlier, go into cell, click on all output, and hit clear. So I'll repeat that, cell, all output, and clear. So at this point, since you are in NiPipe land, all of this is Python. So if you don't know Python or aren't comfortable with it, just sit next to someone and follow along. Yes, you'll be able to hit every cell in this particular case and run with things. But hopefully, if you have questions on concepts, just raise your hand and we'll be happy to answer those things. So the first thing we will do, as we do with almost everything in Python, is import a few things. And in this particular case, we're going to import, let me just make this a little bigger. A workflow, a node, and a function. These are objects, these are Python objects, and what a function allows us to do is to literally wrap any arbitrary Python code as a node in a data flow. So you could have the function, and since Python is a general purpose programming language, use if this then that, which is a service that's available on the web, to even make your coffee at a certain point in a workflow. So a generic Python function is very, very powerful. It can do a lot of things. And this function interface allows you to wrap a generic function. So, but we will do something much, much simpler than making coffee. We'll add two numbers. So here we're defining a Python function called sum. We're adding a and b. And then we create a basic workflow. And these are the constructs that you can use for almost every workflow. You create a workflow object, you have to give it a name. Names are important in NiPipe. So there are no nameless things in NiPipe. No nameless faces. Names are, inputs are named, outputs are named, nodes are named, workflows are named. right, Chris? Everything is named? Okay. So workflow, we've called it hello, and then we create this construct called node. So we are wrapping an interface in a node. So that's a distinction that's important conceptually, that we have interfaces, which you can run and use as described on the help page. And they run literally directly on the shell that you're in. A node creates a working directory for an interface and encapsulates all its outputs within that working directory. So it creates a layer around an interface to create isolation. Why is that useful? There are interfaces that override things. My favorite example is the feat script. The feat script keeps overwriting the same file about 5 times along the way, and it's the mask file that's created. So if you wanted to go back to a certain previous stage of it, you can't. It just overwrites things. With workflows, by creating encapsulation, you can create stages of things. Another example is SPM. SPM uses the spm.mat file as an object store, and it keeps updating that object store as it goes along. A NiPipe workflow with SPM separates out model estimation and contrast estimation that allows you to inspect those objects before or after the estimation. In a standard SPM practice, that would all be merged into one. So it's a better way of capturing different stages of things. Okay, so this node wraps this interface. We tell this function interface that it should expect 2 inputs, A and B, so names. And those names refer to the actual variable names that are being used in the function. So we define the sum function with variable names A and B. These input names refer to that. As of the last release of NiPipe, you don't have to provide the input names. It automatically figures it out from the function definition. But with any Python function, and as with the command line, it doesn't know how to name an output. So we tell it that the output for this function is going to be this word called sum. So those are all names. We assign the function keyword to sum, and we give this node a name. We call it A plus B. The node is assigned to a variable called adder, and the way you set inputs to this node is simply by going adder.inputs.a and adder.inputs.b equal to 3. We add this node object into a workflow, set a base directory, and run it. And we can look at the outputs of the node. So if I run it, it says sum equal to 4. Python does the right thing when you add 1 and 3. So that's a very basic single node workflow. Well, most workflows don't have 1 nodes, so let's connect a second node.
So I tried changing the name of the workflow and things crashed, but the name of the workflow is not even so for example, if I make it hello 1,
I'll change it to hello 1. So if you've moved along to a different place, that would be different. But at least for just this cell where we are talking about this, changing the name of the workflow would be completely fine. Okay. So let's add the second node. And it's a simple node. It takes 2 inputs and creates a list object out of it. And as before, we create a function node. And I'm going to actually, before I go further, go back and switch to hello again. Yeah. Create a function node, give it the input names, give it some name, give it a name for the output, create. So you'll find that this pattern repeats itself, which is you construct an object, you insert an interface into it, you give it a name. But now it adds this other thing. How do I send data from one node to the other? And that's where this idea of named inputs and outputs comes in. So remember, for the adder node, we had created the output name sum. Right? And now we have this input name for this concatenator node called A. And this connect statement simply takes the output of one node and pipes it to the input of another node. And this is literally where things like make break down. The idea behind make is that you can get a lot of inputs coming in, but there's no way to segregate those inputs directly. You have to either specify very explicitly that these are the inputs I want. The idea of multi-valued inputs going in, which are separated by different things, requires a lot of work on the user's part to specify those things. Flexible lists, you have to use Unix glob-like things and other things to separate them out. What we are looking at is a workflow where any given input, any given node could have inputs from multiple nodes. So it's a graph. And make is great for a graph processing. And if you told it that these are the objects I want, it's great for compilation. It's a really nice workflow engine from that perspective. But it requires a lot of work to handhold the objects that you're sending it at any given stage. I don't know, how many people here have created make files? Okay. They take a little bit of work, but they're very, very powerful to do certain things. Okay, so we can add this node and we can run this second workflow, and it says, well, I have an output. We have taken the output from a workflow, concatenated it with another input, and we've got this list for 3. So let's add another node. We'll call it +1. So this takes whatever input and adds 1 to it. And if we do this, I'm going to scroll down. NiPipe says, we have crashed. There's an error. And when NiPipe crashes, it creates a crash file that you can look at. So often we are running these things in an HPC. We are not constantly monitoring these things except during development phases. So we want to look at what happened when things crash. And I'm going to use this NiPipe CLI. There's a little thing with Unicode decoding and environment setup that's not working. So if you're running this, before you hit enter on that cell, delete everything and just keep it at !NiPipe CLI crash space crash star. And if we do that, it will list the output of this crash file, which says these are the inputs I got, and what's important is this traceback. And what we did was we were trying to add a single number, an integer, to a list, which Python doesn't accept. So it tells me type error can only concatenate list, not int to list, which is a standard Python error. So for those who are not very familiar with Python, Python errors kind of go from bottom up. So you want to scroll down to the bottom of the traceback to see the error, and then you keep going up. So how do we do this? Well, this introduces the next concept, which is this idea of a map node. What map nodes do is allow you to execute a particular command on multiple inputs. So if you think of an FSL command like bet, if you gave it a list of files, it'll error. It won't be able to do anything with a list of files because it expects one file at a time. What the map node constructs allows you to do is to tell the interface, when you're getting this input, run yourself separately on each input. So it's like a for loop, but it is like a for loop that expands out that interface for each operation and then collects all the results back. It's a very simple form of map reduce. So it maps out the operation and reduces it back. So let's take a look at how we would do it with a map node. The construct for a map node is exactly the same as we did before. Instead of node, we are using map node, but we add this additional attribute called iterField. What iterField tells map node is, whatever input you're getting on this port, iterate over it. So that's how map node gets to run different things. And we're not going to go into details of iterField, but you can have parallel inputs or parallel sets of inputs that you would run in parallel. So it can make sets of inputs that it will run the interface over separately. Classic example for that would be something like masking a realigned functional MRI file with a different mask. So you have a functional MRI file, you have an associated mask, and you want to mask So for every run, there's a file and a mask, and you can apply FSL Maths or some other tool in parallel for each of them. Okay, so let's add this. We have the +1 node. We create this workflow, and now we can take a look at the outputs. And instead of 4 and 3, we have 5 and 4, which is what you would expect if you're adding 1 to a list of numbers with 4 and 3. Okay. So now we have this concept of connecting nodes, which are through named ports. We have this concept of a map node, which allows you to iterate over a set of inputs on any given port. But one of the most powerful things in NiPipe is this idea of graph expansion, that you can take a subgraph and run that entire subgraph over a set of inputs. And that concept is called iterables. So on this first node, adder, we set iterables. We say that the input to adder can take values 1 and 2. Now this is all very arbitrary at this point. It can do multiple things. You can create 1, 2, 3, 4. The inputs to B is still 2. So what we expect this to do is for each value in A, run this entire graph. So we can take a look at this. So it runs it. This is what the basic workflow looks like. It's still a 3-node workflow. And this is what the workflow with iterables looks like. So you can see that the pattern is repeated twice because we set the input A over 2 values. Yes?
So this is how you would, for example, analyze several patients?
That's one example. So if you have a pre-processing workflow, you want to run it over multiple subjects, you would set an iterable at the beginning of the workflow. We often use the subject ID as a special node called an identity interface, which I can get into later on, and then set iterables on it. But the nice thing about NiPipe is you can introduce iterables anywhere in the graph. So this is like writing multiple for loops all over. So let's say you were doing pre-processing and you wanted to smooth the data with 3 different kernels. Or you were doing machine learning and you wanted to use 10 different models. You can easily add this iterable to any sets of parameters on any node. And that's what makes iterables really powerful. So we're going to add it to a second node. We're going to add it to node B. Here, and then we're going to look at that graph again. So let's take a look at this image. So you see this image where you have 2 branches from the top level iterable, and then since we added iterables on the second node, you see a separate branching happening at the second level. Right? So each branch itself has split into 2 branches. And all we did was add iterables to a second parameter. So often when you do these things, you want to pull and collate the results back together. That's where the idea of a join node comes in. And semantically and conceptually, node, map node, join node all form the same construct. They wrap around an interface, you set some parameters for it, and you work together to do this. So in this case, what we're going to do is this join node will not only pull things back together, but it will also apply a function to those things pulled back together. So we have this merge and scale data function. Again, these are completely arbitrary functions that we have. Here, we're using NumPy to create an array of the data, multiply by 1,000, and then convert to a list. But this also gives me another pointer to point out. So when we define functions, a NiPipe function could execute on a remote cluster, right? It can go to any node. Often when we write Python scripts or any other scripts, we import packages right at the beginning and use them throughout the script. Now, if you were to take an arbitrary function out of that script and send it to the remote cluster, it wouldn't know that those functions exist or are out there. So when you create these NiPipe function definitions, we recommend that you add import inside the function itself. So you can see over here that we are importing NumPy inside the function. Now, there are other ways through pickling and other things where this wouldn't necessarily be an issue, but this is a simpler version because what we do is we actually take the entire code source and send it around and reconstruct that object on the other end. So there are other Pythonic ways of doing this. This was scalable in the sense that the function remains readable as it goes across, as opposed to getting pickled, which makes it harder to read. So, but for those who want to do that kind of thing, Cloud Pickle is an excellent package for doing that kind of pickling. So let's run this. And now we can take a look back at not just the outputs, but the graph of this function. So at a simple level, it's still a linear, this is not really a graph, it's a 4-node linear workflow. But this is what the full execution graph looks like. So we had iterables at 2 levels and a join node. So you expand out, so the initial iterables expands out to 2 branches. Those 2 branches itself become 2 more branches, and then the join node pulls these back into 2 branches. So within a set of fairly simple constructs, you get a fairly powerful workflow engine. Okay. The other pieces that we have over here, we're going to run and execute this workflow. And it said it took 172 milliseconds. You're going to point to a different location, run that workflow again. This is a very quick workflow. And we'll run it again. And you'll notice that the time to run it the second time is much quicker than the first time. And that's because when NiPipe runs, it caches the output of every node in the working directory. And when it does that, all it needs to do is pick up those results and check that the inputs haven't changed. So if you're maintaining your working directory, it doesn't rerun things when you change, let's say, a node at the end. It's kind of like a Docker file build for those who have built Docker files. If you only change one line, it'll go to that point and only build layers from that point on. So this is very useful if you have a caching setup available. Now, in many cases, it's going to be a balance between whether your storage costs more or your compute costs more. So if storage is not an issue, you cache the output, and then you can reuse things. If your storage costs a lot, which is what we do. For us, compute is cheap relative to storage. We create the working directory in a temp thing, and we don't avail of NiPipe's caching when we are computing. They're only effective for that session of running things, but then our scratch directory gets wiped out every 3 weeks. Okay, so here is where I'm hoping there's at least one Python person at each table. We're going to ask you to write a little workflow. So you have all these concepts. Yes, you can hit solution and cheat and peek. Maybe peek is the better word. But the idea here is to construct a simple set of things. This will also try to help you with your Python function definitions if you haven't defined a Python function before. And it guides you stepwise to work on some of these things. So if you have questions or run into errors, raise your hand. This should take 15 to 20 minutes-ish for the first exercise to work through. Before, yeah.
If Python breaks in some moment, that the function that has been already computed, they remain cached too?
If the node breaks, under special circumstances, parts of it get cached, but not always. So generally, wherever the node crashes, that will restart from scratch. But there are certain nodes which allow this internal state of history and can pick up from that point on. It's not a NiPipe thing, it's more the underlying tool. And when that underlying tool supports it, when we construct these interfaces, NiPipe has semantics to say continue from wherever you left off. Yeah.
Cool. This is only going to take a couple of minutes. So we learned how to make a very simple workflow, but as soon as you start building workflows, you have built workflows before, you understand that those can be much more complex and they can have many more steps. So here I just want to show you a couple of workflows that have been developed in our lab. And the main purpose of this is just to give you an example of how you can manage complexity of these workflows in NiPipe. So for example, this is So this is MRIQC, which is a tool developed by Oscar Esteban in our lab, and it's basically doing quality control, both metrics and visual reports for structural, T1, T2, as well as functional data. And to extract quality metrics, sometimes you have to do some pre-processing. So as this thing is showing, let me just make this bigger. Or be confused. Okay, cool. As this is showing, when you have input raw data, you can calculate some quality metrics on that raw data, but some other metrics, for example, require you to have a head mask or tissue segmentation and things like that. So we do have to do some pre-processing. So to do this, Oscar has developed a workflow, and this workflow might seem a little bit overwhelming to begin with. And if I learn, a little bit overwhelming to begin with, but if you look at it, it actually is built from those blocks here. You see this ant skull strip workflow, spatial normalization workflow, and there's a head mask workflow, and an air mask workflow, etc., and computation of IQMs, which are the quality metrics, and then reports. And each of these big boxes is a workflow in itself, and you can divide your code and your workflows into smaller sections and have them in separate files and manage them separately. And you can also make those sub-workflows exchangeable. And you really don't have to learn anything more than you already do know, because a sub-workflow is exactly the same as any other workflow, and you can treat workflow as nodes, and you can add them and connect between workflows or between nodes inside workflows. So that gives you a lot of flexibility in how you can manage your complex workflows. And NiPipe itself, if you go to the website, nipipe.org/NiPipe, includes some predefined workflows that you can reuse in your code. So if we go to workflows, for example, there's stuff for pre-processing fMRI and stuff like that. But you can also start building a collection of workflows for your purposes, for your projects, for your lab, etc., etc. So all I'm trying to show here is that with the system of sub-workflows in NiPipe, you can basically divide your code base into meaningful units, so you don't end up with the one 1,500 lines long file that has all the steps that is quite hard to navigate and easy to get lost in. So that's all I have. I know that everyone is hungry.
So the only thing I wanted to add was that you would never write that workflow that's in exercise 1 ever, because that's one line of Python NumPy code to actually do it. But the general exercise is really about understanding this notion of inputs and outputs and how you can use the concepts to do it. I would highly recommend that people use the tutorials. So each concept that we studied has its own notebook in the basic concept section of the tutorial. And so that goes through each concept in depth, in more detail, that you should go over if you want to create NiPipe workflows. That being said, there's a whole bunch of workflows available over there that, as Russ referred to as clear glass boxes.
Yes, that's the aspiration.
Yes. So you can reuse those workflows, whether through MRI QC or fMRI prep or a whole host of other things out there. So with that, we're going to stop, and Ariel has to make a couple of announcements.
Yes, so before we go to lunch, I'll just make